Hello and welcome to this video demonstration of our project Smart Greenhouse. This IoT project aims at automatically managing greenhouses. Our project has three main goals: automatically watering each plant depending on its water requirements and its soil moisture, automatically controlling the temperature so that it is suitable for the plant, and automatically updating the water requirements of each plant depending on the temperature. Each greenhouse contains one temperature sensor and one cooling and heating actuator used for controlling the temperature. The greenhouse is divided into several zones that contain a specific type of plant. Each zone has a specific acceptable temperature range and a moisture minimum value for it to grow properly. Each zone contains one moisture sensor and one irrigation actuator to control the irrigation of the plant. For this project, we have coded the following microservices that we will describe one by one. The service and device registry is used to register services, users, their greenhouses, their zones, and their devices. Each service and devices periodically updates its registration in the catalog. The catalog periodically deletes devices and services that have not updated their registration for 80 seconds. To manage its greenhouses, the user first needs to connect to the Telegram bot. We start from an empty catalog. You can see the catalog terminal in the top left corner, the Telegram bot terminal in the bottom left corner, and the Telegram interface on the right. The user will use the command create user to register itself in the catalog. You can now see the user appear in the catalog. The user can then create a greenhouse with the command create greenhouse. You can see the greenhouse appear here and its ID appear in the greenhouse list in user list. Then they can create a zone in a greenhouse using the command create zone and all the required arguments. You can now see the zone here and its ID here. We use simulated sensors and actuators to be able to simulate easily all the conditions of our system. The cooling, heating, and irrigation actuators consist of a simple code that updates one of its attributes depending on the actuation command. I will now explain how each sensor works. The temperature sensor simulates the temperature of the greenhouse, considering whether the cooling and heating actuators are on or off. If the heating actuator is on, the temperature is decreased by a random amount. If the cooling actuator is on, the temperature is decreased by a random amount. Otherwise, it is randomly increased or decreased. The moisture sensor simulates the moisture of the zone, considering if the irrigation actuator is on or off. If the irrigation actuator is on, the moisture is decreased by a random amount. Otherwise, it is decreased by a random amount. We use two different control strategies, one for temperature and one for irrigation. For the temperature control, we activate the cooling and heating actuator depending on the received temperature measure and the greenhouse's temperature range. To compute the greenhouse temperature range, we take the range of each zone of the greenhouse and we take the minimum of the upper bounds and the maximum of the lower bounds. If the temperature is below the minimum value, we activate the heating actuator. If it is above the maximum value, we activate the cooling actuator. Otherwise, we deactivate both actuators. We can see here from top left to bottom right the catalog, the temperature sensor, the temperature control, and the cooling and heating actuator. We can see the device registered in the catalog here for the ID and here. We can see that when the temperature is published by the sensor, the temperature control gets it, compares it with the range it has get from the catalog. Here it sees it's acceptable, so the actuators are all both turned off, as we can see in the file actuator. For the irrigation actuator, we activate the irrigation actuator depending on the received moisture measure and the zone moisture threshold. If the moisture is below the threshold, we activate the irrigation actuator. Otherwise, we deactivate it. We can see here from top left to bottom right the catalog, the moisture sensor, the irrigation control, and the irrigation actuator. We can see that when the moisture sensor publishes a value, the irrigation control gets it, compares it with the threshold it has, and here it sees it has to add water, so it tells the irrigation actuator to start. For storing data, we use ThinSpeak and 6-speak adapter. We can see from top left to bottom right the catalog, the temperature sensor, the moisture sensor, and the ThinSpeak adapter. When ThinkSpeak adapter receives a message from a new greenhouse, it automatically creates a new channel with one field for the temperature, one for the cooling and heating actuation, one for the irrigation actuations, and one for the 5 first zones of the greenhouse, if they exist. We cannot add more zones because a channel is limited to 8 fields on ThinkSpeak. The greenhouse and the zones are then updated in the catalog with the following channel and field information. If a new zone is added to a greenhouse and we have less than 8 fields in the channel, a new channel is automatically created. The zone is then updated in the catalog with its field number. On ThinkSpeak menu interface, we can see that the data is updated on the corresponding graphs. We also created a combined graph for the moisture to plot all moisture levels on the same plots. For this, we used MATLAB visualization with these codes. We compute some statistics on the data stored in ThinkSpeak to update the moisture threshold of each zone depending on the average temperature of the last 5 days in the greenhouse. Every 5 days, for each greenhouse, we get the temperature of the last 5 days from ThinkSpeak and compute the daily average. If it has increased over all 5 days, we increase the moisture threshold of each zone in the greenhouse. If it has decreased over all 5 days, we decrease it, otherwise we do not update it. We can see from left to right the catalog, the ThinkSpeak adapter, and the temperature monitoring. In order to show this code working, we had to modify the code to keep it from waiting 5 days before each update. We comment in the following lines. The code computes an update of 0, which is coherent because we have not gathered data for 5 days yet, so it behaves as if the daily average temperature was constant. For user awareness, we used Node-RED and Telegram bot. We use Node-RED for graph visualization. We launch it with Docker using a volume. On the Node-RED interface, we can see the flowchart we used. We collected different data from ThinkSpeak and plotted different graphs. For each user, we plotted temperature, combined moisture, heating and cooling status, and total irrigation. If we go on the user dashboard, we can see these different plots for the first user, and we made also an example for a second user with these plots. The Telegram bot provides the user with several commands. The command help gives the list of possible commands. Clicking on the command get greenhouses, we get the list of greenhouses of the user. Clicking either get zones or on the button of the zone here, we get the zones lists of the greenhouse. Then, clicking on a zone, we get the zone information. We can also use this command to do this. The command update moisture is used to update the moisture threshold of a zone. We can see in the catalog that the moisture threshold has indeed been updated. Commands are also available to delete the user from the catalog or to delete a greenhouse or a zone. We'll see how to delete a zone. So first, we can see here that the zone is in the catalog and here in the list of greenhouses. Now, if we execute the command, we can see a success message here. And here, the zone 2 has disappeared. We have seen the main features of our platform. Thank you for your attention.